Hi guys, welcome to the next lecture. In the previous lecture, we learned about the type of functions we can have: one-to-one, on-to, many-to-one, into. And there came one situation when I said that a function could be one-to-one as well as on-to, right? So we will pick up the threads from there today and work it up. We will talk about bijective functions. Now, what is a bijective function? The term bijective suggests that there are two things happening altogether. Bi. So bi would consist of injective and surjective. So a function which is injective as well as surjective, that function is called a bijective function. Let's understand the scenario. What's going to happen in that case? Suppose this is a set A and this is a set B, and we have a function from A to B. F is a function. We are saying that it's a bijective function and we want to analyze under what situation this will happen. So bijection means that it has to be a one-to-one function. So let's say this is a one-to-one function. From one-to-one function, what you must have understood is that in case you have three elements here, three distinct elements here, they will give you distinct outcomes. There cannot be any two inputs giving you the same output. So, hence, if you have elements, three elements in the input, you will definitely have three different outputs. Suppose this is the scenario. Now, one-to-one function says that you can still have idle elements in the codomain. The range doesn't have to be equal to codomain. But when we say that the function is surjective as well, then under that scenario, we cannot have an idle element in the codomain because surjective means that the range should be equal to the codomain, right? So I cannot have this idle element here. This element here should have a pre-image, and of course it has to be a unique pre-image. And also for the definition of a function itself, I cannot map this element to some other element, the first three elements that we had here, for a simple reason, then it will not be a function itself. Always remember, one to many is not a function. By the definition of a function, there has to be a unique image. No input can have two images, right? So we got to have a unique pre-image here because it's a one-to-one function. What is this giving me? This scenario is providing me a certain different kind of relation holding up. What is it? It is giving me that one element here, say this is x1, this is x2, this is x3, this is x4. x1 is associated to y1, x2 is associated to y2, let's say, and x3 is associated to y3, and x4 is associated to, say, y4. What is happening here? You have a sort of one-to-one correspondence. A particular x has a special relation with a particular y. It's a one-to-one correspondence. When I am looking at x1, I know that x1 will be related to y1. When I'm looking at x2, I know that x2 is related to a particular y2. And I know about y1, y2, y3, y4 as well. I know that y1 is particularly associated with x1 and so on and so forth. So what does it tell us? It tells us that there is a one-to-one correspondence of elements from A to B. One-to-one correspondence is a very important concept, and this is related to bijection, of course. This is happening because the function is bijective. It is one-to-one as well as on-to. And therefore, there is a particular element associated to every x and it's unique in nature. So what is happening here? You have, by the definition of a function, you have a unique image and you also have unique pre-image because the function is one-to-one. It's a one-to-one mapping. So therefore, you also have a unique pre-image. Now the function is onto. So that means range must be equal to the codomain. So these three things are happening together. And together you got to think, what is it implying? It is implying that you have no ideal element in the domain and no ideal element in the codomain. And there is a one-to-one correspondence of each element in A and B. This means that the number of elements in A, which we also called cardinality of A, number of elements in A, they have to be equal to the number of elements in B. That is, cardinality of A and cardinality of B needs to be equal for this to be a bijective function. Whenever a function is bijective, that means the domain and codomain have equal number of elements, because there has to be a one-to-one correspondence. How will this one-to-one correspondence work if you don't have equal number of elements? You can't have free floating elements in the codomain. You never have ideal elements in the domain. That's why the definition of a function. So exactly same number of elements need to be there in A and B for us to have a bijective function. Now, what is important in this scenario is, see, you have a mapping wherein you are looking from A to B. That's how you were looking, right? But now, since every X has a one-to-one correspondence with some special Y, this means that I can actually move from B to A in the same fashion. B to A is also possible. Whenever you have a one-to-one correspondence or bijection, in other words, that means whether you go from X's to Y's or you come from Y's to X, it's going to be the same thing. And that's what is existence of an inverse for a function. So here, let me add to this picture itself. We can actually define in this situation a function from B, the codomain, to the domain A, and we call it F inverse. So this means that F from A to B is bijective if and only if and only if means that it's equivalent to saying. It is equivalent to saying that there exists a function F inverse which could be defined from B to A. What is required for it? That F should be bijective, because in case bijection will happen, then only one-to-one correspondence will happen. You cannot have a situation like, for example, suppose you have a one-to-one mapping, but not an onto. So this is the scenario. If you have an ideal element in the codomain, do you think you will be able to go from this set to this set? No, you will not be able to, because you cannot have any ideal element in the domain for the existence of the function, right? And when you are moving from B to A, that means B is now your domain. And a domain entry is not mapped with anything. That cannot happen, right? So therefore, one-to-one as well as onto is required for existence of inverse. The same thing can also be expressed as the functions with two-sided inverse are bijective. Now, what do we mean by two-sided inverse? So suppose you have a F inverse from B to A for any F which is from A to B. Now, two-sided inverse would mean that, so you have FA will be an entry in B. And since you have a function from B to A, that means you will be able to apply F inverse to this input FA. Right? FA is an entry in B, and since B is the domain of F inverse, so I can apply F inverse on FA. FA, in case it's an inverse function, F inverse of FA should actually be A, because that's the one-to-one correspondence that is happening. This is only possible when there is a one-to-one correspondence, in other words. Similarly, now you have F inverse B, which is something that you will find in A, F inverse B. You will find F inverse B here. Now, since F inverse B is in A, and A is the domain of F, so I can apply F on F inverse B. What I should be getting is actually F of F inverse B should turn out to be B only. That's the idea of inverse. Okay. This is what is a two-sided inverse. That's what we are saying. It's a two-sided inverse. When is this possible? This is only possible if you think in terms of mapping. So it is A to B. Here goes F. Here comes back F inverse. So here you have A. Here you will have F of A. Here you have some B, and here you will have F inverse B. If this inverse actually exists, then it has to be the case that A has a one-to-one correspondence with FA, B has a one-to-one correspondence with F inverse B. That's what is a two-sided inverse. So we can even quote the same thing like this. Ultimately, what result we have here is a function has an inverse, or F inverse exists if and only if F is bijective. Thank you.